This is a report for experiment major losses in pipe and presented by Group 1.
This is our group member, Lim Zi Hui, myself, Norainun, Basyirah, Nurul, Afifah, and Afiq, Danial.
This is our table of content.
So, introduction of the experiment. This experiment examines significant losses in pipes with a particular emphasis on energy loss from fluid to pipe friction. Using the Moody chart, the pipe friction factor F is calculated by measuring the pressure drop along a straight pipe under steady flow. The finding offers guidance for creating effective pipe systems and maximizing fluid flow in engineering application. The objective of this experiment is to determine the pipe friction factors F, or we call it as resistance coefficients.
For the theory and working principle, we are focusing on, in this experiment, we're focusing on major head loss. So in this experiment, the elevation is equal to 0 as the pipe is horizontal, Z1 is equal to Z2, and the internal diameter is constant for us to control that, so that there will not have any minor head loss, and then so that the total head loss is equal to the major head loss. And there is two equations in this page, which is equation 1 and equation 2. Equation 1 is to determine the pressure loss, and the equation 2 is to determine the major head loss. So there is some of the parameters that we need to determine in this experiment. First of all is the friction coefficient, velocity, density, diameter. So to find the friction coefficient, we need to find out the value of Reynolds number and also the equivalent pipe roughness. This is because friction coefficient depends on these two parameters. So for different type of pipe, they have different equivalent roughness. So we're referring at the right side, which is table 1. Different pipe have different value of roughness. Other than equivalent roughness, Reynolds number also very important for us to determine the friction factors. So we are going to calculate using equation 3 to find the Reynolds number. So we use equation 3, and then when we have already the Reynolds number and also the epsilon equivalent roughness, so we can utilize the figure 1, which is the Moody's diagram, for us to find the value of F by using the graph. And then for the equation 4 is the equation for us to calculate the speed of flowing medium. So we basically will get the value of velocity by using the equation 4. And then the table 2 is the table for us to determine the kinematic viscosity of water as a function of temperature.
For the turbulent flow in smooth pipes, for F, for the Blasis formula, valid for Reynolds number less than 10 power 5, it can be calculated using equation 5, while for the Colebrook formula, the F can be calculated using equation 6. Equation 6 is an implicit formula that has to be iteratively resolved. First of all, you have to estimate the value of F, place it in the formula, and calculate the initial approximation. This approximation is used in the equation to calculate a second approximation. If estimated value is taken from Moody chart, the initial approximation is generally sufficiently accurate, and the values only differ after the third decimal place. The F in turbulent flow also could be determined using a Moody formula, which is equation 7. Alternatively, we can also find F using Moody chart.
For the experiment setup, we have two tube manometer, rotameter, thermometer, gate valve, feeding hose, interchangeable measuring object, digital display for pressure, pump switch and main switch, differential pressure sensor, and then the last one, return hose. For the methodology, the first one, both the feeding and return hose were connected to the tested pipe section, and then the tube was connected to the inlet H1 and outlet H2 pipe section and to the manometer. And then third one, the pump was switched on and the control valve, which is rotameter, was slowly opened to the maximum level to remove air from the pipe section, and the black cup valve on the top of the manometer was slowly opened to release all bubbles in the system and then closed. Then the gate valve was closed to ensure no flow, and the white valve was slowly opened until plus minus 25 millimeter for galvanized steel pipe. Next, step 7, the control valve, which is rotameter, was slowly opened until the water level in the H1 reached the maximum and the manometer H2 reached the minimum level. The value for the maximum reading were recorded. Next, the flow was reduced by closing the valve to take the next reading for 5 different readings. And then the manometer tube was then transferred to the differential pressure sensor, which is gray box, to take the reading for differential pressure at the digital display first screen. If bubble were present in the tube, the control valve was opened to maximum level, and then the gray cup at the box was opened to overflow the water and then closed after no bubbles remain in the system. Step 11, the flow was adjusted back to the previous record. Once finished, all connected tube were removed, the control valve was closed, and the pump was switched off before the feeding and returning hose were changed to another pipe section. Steps 6 to 12 were repeated with various tested pipe. It is plus minus 25 millimeter for PVC 16, and then plus minus 1 for the copper, PVC 20, and PVC 32. After all finished, all connected tube were removed from the system and the control valve was fully closed. And last one, the pump and the main switch were switched off. Next, the result and outcome from the experiment as shown in the figure 3, which is the data for galvanized steel pipe and copper pipe, and the figure 4 is data for PVC 16 and PVC 20. And the last one is the figure 5, which is the data for the PVC 32.
For the discussion, we have compared the coefficients of friction factors for each of the tested pipe and the coefficient of friction from Moody's chart and the calculation using a formula of Basyirah, Colebrook, and Moody's. And then for the table 3 shown is the table for the data for galvanized steel pipe. And then we have below part is the calculation for the parameter needed for us to determine our coefficient of friction. So we have listed down the internal diameter, kinetic viscosity. We have calculated by using the table 2, which is in our theory part, and then the value of kinetic viscosity is calculated by using the method of interpolation. Besides, we use the equation 3 in the theory part to calculate the value of Reynolds number and also equation 4 for the value of velocity. The Q average for this galvanized pipe is 0.0000556 meter cube per second. This indicates that the amount of volume of the water is quite little in a second, but the velocity is actually 0.43 meter per second, and the Reynolds number is 7,210.75. The fluid is in turbulent flow. In this slide shows the figure 6 calculation of friction factors and HR major loss for galvanized pipe. So for this page, actually we have determined the friction factors by using different kind of method: Moody's chart, Bloss's formula, Colebrook formula, and Moody's formula. And then the figure 7 is the Moody's chart for us to determine the friction factors. So we have determined the equivalent roughness, and also we have utilized the parameter we calculated in the previous slide to calculate this. So we can see that the friction factors is actually quite consistent, unless for the Moody's formula is quite different from others method. And also the HR value is 0.036 at average. For the table 4 records the data for the copper pipe, and then it's the same as the galvanized pipe calculation. So we calculate the kinematic viscosity, internal diameter, area of the internal pipe, and we use equation 4 and equation 3 in the theory part to calculate the velocity and also the Reynolds number. And the Q average is 0.00044. And also the fluid in this copper pipe is in turbulent flow also, and the Reynolds number is 45048.36676. For figure 8 is the calculation for friction factor and major losses for copper pipe, and also the figure 9 is the friction factors for copper pipe in Moody's chart. So there is respective value that we calculated using the Excel, and for the friction factors F for the Moody's chart, Bloss's and Colebrook formula the value is very similar, which is 0.021, whereas the Moody's formula is very has a significant difference from the others formula. And also for the HR value, the situation also the same for the Moody's formula, which is very far, which is 0.06 for the HR value for the Moody's formula, whereas for the others is at the average of 0.33 for the HL. From table 5, we have collected the data for the PVC pipe with 20 meter outer diameter, and the temperature is 30.8, and we use the table as the same. We use the interpolation to calculate the kinematic viscosity, and also we calculate the velocity and Reynolds number. So as you can see, the velocity is 1.95, and also the Reynolds number is 42183.7, which is turbulent flow. Same goes to this for the Moody's chart, Bloss's formula, Colebrook formula, and Moody's formula. The figure 10 shows the calculation of friction factors, and also figure 11 shows the Moody's chart for this PVC pipe with 20 millimeter outer diameter. And also Moody's formula still giving a significant difference value, friction coefficient, and also major loss. And for the others method, Moody's chart, Bloss's formula, and Colebrook, they're giving the value of 0.022 for the friction factors, and also HR value of 0.25. For the table 6, we collected the data for PVC pipe with 11 millimeter outer diameter. Temperature is 29.5, and we calculated the kinematic viscosity, the area, velocity, and also Reynolds number. So velocity is 1.14, Reynolds number is 17582. It's also turbulent flow, and the Q average is 0.000138. It's the same for the figure 12 and figure 13. So the figure 12 shows the calculation of friction factors and also the major losses. For the Moody's chart, is shown in the figure 13 on how we are going to determine the friction factors. And also for this, when we refer to the figure 12, right, we can see same situation happens here. So the Colebrook versus Moody's chart, they have similar friction factors and HR value. But for the Moody's formula, which have a significant difference in this situation. And the F is average at 0.026 for Moody's chart, Bloss's formula, and Colebrook, and the HR is 0.145. For the Moody's formula for the F value is 0.005, and HR is 0.028, which is very far away from the value. For the table 7, we collected the data for the PVC pipe with 32 millimeter outer diameter, and the temperature is 32.5. So we use interpolation to find the kinematic viscosity, and also the velocity is 1.11, and Reynolds number is 40980. So the flow is turbulent. The figure 14 shows the calculation of friction factors, and major losses, and figure 15 shows the friction factors on how we are going to determine in the Moody's chart. So at Moody's chart, Bloss's formula, and Colebrook, you can see that the F value is similar. It's around 0.22, and the HR value is 0.04 until 0.05 at the average. But for the Moody's formula, it's very far away, the values, which is F equals to 0.00399, and HR is 0.008.
So for the possible reasons for difference in their values, first there are estimation of pipe roughness. So the estimation of pipe roughness may be inaccurate. This will lead to deviations of the calculation. In addition, the ballistas assume an ideal condition, while in reality all the parts have a more constant roughness throughout distributions. Hence, the measurement error. From the experiment itself, there may be an error such as the error from the instrumental calibration. This is caused by the inaccuracy of the flow meters. Other than that, the temperature may also have a fluctuation that may affect the fluid viscosity and density. Thirdly is the assumption of method use. So from the Moody's chart and Basyirah equation, it assumes steady flow and no interest or exit effects. But in the experiment, there might be interest losses or valve that disturb the flow. Other than that, the goal group may have different results if there is an approximation used to simplify it.
For the next discussion is about the rank the pipe in ascending order trend based on their major loss value obtained from the experiment, and briefly explain the factor that influence the pipe ranking selection. So for the pipe rankings, the first one is galvanized steel pipe, second PVC pipe 32mm, the third PVC pipe 60mm, and fourth one the PVC pipe 20mm, and the last one is copper pipe. The factor that influencing the pipe ranking selection, the first one is about the pipe material, which is the galvanized steel pipe typically have a smoother internal surface compared to PVC and copper pipe, leading to the lower friction and those smaller major losses. Copper has a rougher internal surface due to corrosion or manufacturing that contribute to higher friction losses. The second one is about the pipe diameter. Larger diameter as the PVC 32mm result in lower velocity for a given flow rate, that reducing the frictional losses compared to the smaller diameter pipe as the PVC 60mm and 20mm. The third factor that influencing the pipe ranking selection is surface roughness. Smooth pipe like the galvanized steel pipe have a lower roughness that leading to the less resistant and less energy loss. Copper has a higher roughness that significantly increasing frictional losses. The last one factor is flow velocity. Higher velocity increase major losses due to the quadratic relationship between velocity and head loss. Smaller diameter pipe as the PVC 60mm is experience higher velocity for the same flow rate, resulting in greater friction losses.
Next is the factors contributing to errors and the possible recommendations. So first is the parallax error. This happens when the eye is not perpendicular when taking readings, and black contact may be wrong. Next is the foundation of the manometer. The accuracy of data is disturbed as there is an absolute flow rate during the experiment. Next is the presence of air bubbles, which will cause the experiment and give a wrong value of data. The recommendation are make sure the eye level is perpendicular to reading to avoid parallax error, removing air bubbles to get accurate value of data by opening ventilation to allow overflow of water before experiment, and lastly take an average readings for all side of data to get more accurate readings.
For the safety procedure, number 1, we can handle water carefully to avoid spills and spilling hazard. Number 2, we should wear PPE such as lab coats, gloves, and closed-toe shoe. Number 3, we have to make sure eye is perpendicular to the reading of the manometer to get accurate reading and avoid parallax error. And lastly, we have to get rid of the bubbles in the tubes to get accurate reading.
So in conclusion, for each diameter, water flow rate, pipe bands, and pipe diameter each have its own different loss coefficient and minor head loss. The findings demonstrate that fitting geometry affect loss coefficient with larger losses occurring from acute bands and diameter changes. Smaller diameter result in larger losses while minor head losses rose with lower velocity. The correctness of numerical formula was confirmed by close match between experimental data and the theoretical expectations. All things considered, the experiment resembles crucial pipe shape, flow rates, and fitting types are to reducing energy losses and maximizing fluid transport efficiency.
This is our reference. This is our Excel calculation link. Thank you. Thank you.